Okay, so for this question, it says that segment BC weighs 210 pounds per feet, segment CD weighs 300 pounds per feet, and P1 is equal to 6 kips. And then it asks us to find the magnitude of the resulting internal normal force at the cross section through point A. So it's really easy. All we have to do is first we have to draw our free body diagram, very original. But what we are doing is we're drawing our free body diagram at point A, right? So this is point A. So if we look back at the picture, it's sort of like cut here, right? Maybe in a different color would be better to see. It's sort of cut here. So what we're going to have is we're going to have our internal force at A, so we'll call this in A. Then we have a couple of things we can just put on from our picture, like these two 3 kips, 3 kip forces, so 3 kip, 3 kip, and then our P1, which in our case is 6 kips, so 6 kip. Now we have everything that's given except for the weight. So the weight is going to act at the centroid of this, which very luckily is A. So we'll call this the weight of CD. And then we'll have a very similar situation here with the weight of BC. Now we know our weights in pounds per feet, but that's not very helpful because everything else is in kips. So what we're going to do is we're going to call the weight of CD is equal to, what is it, 300 pounds per feet, pounds per foot. So we're simply going to multiply that by the feet to find the weight in pounds, which in this case is going to be 4 feet. Remember, it's not going to be 8 feet. A common mistake is to say it's 8 feet, but it's only 4 feet because we're only looking at this square right here. So this is going to be 300 times 4 feet, and this is pounds per feet, whatever, it doesn't matter, which is 1,200 pounds, which is also known as 1.2 kips, which is very helpful for us because everything else is in kips. And then the same process, but for BC, we're going to get 210 pounds per foot is equal to 210 times, and this is going to be the whole distance, so that's 10 feet because that's our whole distance in the free body diagram. So it's going to be 10 feet, which is 2,100 pounds, which is known as 2.1 kip. So then if we come in here and we replace our variables with the values, so 1.2 and 2.1, then we have a free body diagram that is very nice and easy to compute. So we're just going to have the sum of, we'll do the sum of forces, and this is in the y direction, I just wrote it horizontal, is equal to 0, is equal to NA minus 1.2 minus 6 minus 6 minus 2.1, which turns out to be 15.3 kip, and that is the answer for A, 15.3. Okay, now for part B, it says we have this figure on the left, and it says the column has a mass of 200 kilograms per meter. P2, P3, and P4 are all given, and it asks us the same question: determine the magnitude of the internal normal force at A. So we're going to do the same thing. I'm going to draw the free body diagram. I'm going to do it horizontally because space restrictions. And then we have this little cutout. This will be point A, right? So we'll have our normal force at A. We'll have our little boop, our little cutouts, boop. And this is going to be P4, which we know as 6 kilonewtons. 6 kilonewtons. Then we have another one of these little fins, and these ones are 7.5 kilonewtons, and then the same 7.5 kilonewtons. And then we have our P1, which is 9.5 kilonewtons. And now the only thing we're missing is the weight. And for that, we will, again, at the centroid, which for this would be at 2 meters. But again, we're cutting it at A, so it's going to actually end up being closer to like around here. But that's not really important for this question, but this will be the weight of the column. Now, in a very similar process, we need to find the weight of the column. So we have 200 kilograms per meter. So we're going to write this as 200 kilograms per meter times, what is it, 3 meters. And again, we're using 3 meters because that's the difference, or that's the height. We're only doing this box, right? We're not including that bottom. So times 3 meters, which ends up being 600 kilograms, right? Because the meters cancel out. And then the only thing we have to do is kilogram is not a weight, it's a mass. So what we have to do is we're going to convert this to a weight. And so what we're going to do is 600 kilograms times the gravitational constant, which is in meters per second squared. And you'll get an answer like 588, or actually you'll get an answer like 5,880. And this will be in newtons, right? Kilograms meters per second squared. We're going to write this as in kilonewtons, because again, everything else is in kilonewtons. So this will be 5.88 kilonewtons kilonewtons. And again, we have a similar situation where all we have to do is sum our forces up. So we'll end up with NA is equal to 6 plus 7.5 plus 7.5 plus 5.88 plus 9.5, and it'll give us a nice answer of 42.4 kilonewtons.